Okay, sorry about that. 5.10 exponential functions and their inverse logarithmic functions. So we've spoken about logs and exponentials being inverses. You do need to understand that each base, so here's a base 2, each base has its own logarithmic function that is tied to it. Okay, so if I want to find this inverse, I do what we've been doing so far, swapping it. And then the inverse of a base 2 exponential is a log base 2. So if I take the log base 2, and on this side I just get the log 2 of x, and then on this side the reason I'm doing that is so that that y, that exponent, will come down. So that expression is the inverse of this exponential expression. If the base changes, then after I swap x's and y's, then the log will also have to change, because the log's base needs to match the exponential base. So here I'll have to take a log base 3. So then I get the log base 3 of x is equal, and on this side the exponent drops, and that's a y. So that's the inverse. Okay, so what happens then if I start adding and subtracting and some other stuff? So in this case, you swap. Okay, you look at the exponential expression, it's by itself, so I can bring this exponent down by matching the base of the exponential with the base of the log. So I get the log 2 of x, and on this side the exponent comes down, but the exponent is y plus 2. So that leaves me one more step, so I need to subtract 2 on both sides. Now I would say line up the negative 2 over here to subtract 2 and write it this way. I think that's a little more clear than the other way. So this is what I would do. You could say, okay, let's line up the negative 2 sort of over here, and then you would write the log 2 of x minus 2 is y. Now it's not real clear right now if this is a subtract 2 or is this, supposed to be an x minus 2. And it's the first, so then you would have to have brackets around it here, and you can see it's just a little messier. Okay, so out of habit I usually write it this way. It's not wrong to write it the other way. So what happens on this one then? Well, still swap x and y. You need to isolate this exponential base. So before you start worrying about the exponent, you have to do this. Now when you take the log base 2, because the exponential expression has a base 2, now you would need to write it like this. This is x minus 1 in brackets, and on this side the y comes down, so there's nothing left to do. Okay, so be careful how you write things, and be careful with where's the plus 1 or the plus 2, where is it located? It does make a difference. Let's go graph a couple, and I'll try to do the exponentials in red. So let's just graph the y equals 2 to the power of x first. So graphing that. So negative 1, 0, and 1. So at a negative 1 I get a half, at 0 I get 1, at 1 I get 2. Yeah, let's add 2, 4 there, just so I have another dot. So at a negative 1 I'm at a half. 1, then at 2, and then at 4. So the exponential function looks like this. Okay. Well, to find an inverse, if you have a table, you can just swap x's and y's, right? So this function, this inverse of that exponential function would have the following ordered pairs, because you swap x's and y's. So in blue, this is the inverse of what's in red. So at a half, I'm at a negative 1, then 1, 0. At 2, I'm at 1, and at 4, that's 3, that's 4, I should be at 2, and so the graph looks like this. Now, an exponential has a horizontal asymptote, right? I guess we're going to answer this question over here. An exponential has a horizontal asymptote, and that would be at y equals 0. Well, if you really swap x's and y's, does it make sense then that the log would have an asymptote at x is 0? Well, that would be a vertical asymptote. And you can see that it does appear to have that as an asymptote. Okay? Just keep in mind that if you swap x's and y's, these y values here never quite get to 0, right? So you're just approaching it closer and closer and closer. So if you mirror that, then this blue line will get closer and closer, but it will never get there either. So hopefully it makes sense that way as well. Okay, let's look at the domain and the range then. So in red, okay, making sure I was in red. The domain for the exponential function is going to be all real numbers. The range for the exponential function is from 0 to infinity. And some of you guys write that like y is larger than 0, which is fine. Okay, it's probably easy. Alright, so what about the inverse? Well, again, you can swap x's and y's, so domains and ranges should swap. So the domain should be from 0 to infinity. Okay, I guess this is one reason I use 0 to infinity. Well, that means x greater than 0. If you write it that way, you're okay. So again, if you swap x's and y's, then you're perfectly fine if you do that. And the range then would be the domain of the original, so all real numbers. And that matches our picture, because the domain is clearly, we don't quite get 0, but anything to the right of 0 we're allowed to use and we'll get values, so that makes sense. And then here the range, well, it goes to a negative infinity here, and although it goes up slowly, it does keep going up, up, and up, so eventually it will get to infinity here as well. Okay, so that's it. Alright, next one. So we've got a little bit of a change here, so 2 to the power of x minus 3. Oh, forgot to do this. Let's find the actual inverse as well and see what that looks like. So swap x's and y's, so x is equal to 2 to the power of y. It's isolated, so we can take a log base 2, so log 2 of x equals y, so let's put the y here. So this is the function that was graphed here. So that's the general shape for a log. Okay, it has an asymptote that's vertical, and it goes down this way, and then it slowly continues to go up. Alright. Okay, in red, we'll go a little bit faster for this. So we're going to use a -1, 0, and 1, and we'll use 2 as well to get a slightly more, a larger value over there. So that's a half minus 3, -2.5. So at 2 to the power of 0, that's 1, and 1 minus 3 is a -2. 2 to the first is 2, so 2 minus 3 is a -1. 2 squared is 4, so 4 minus 3 is 1. Okay, so this took the graph and shifted it up or down 3, right? So the asymptote that used to be y equals 0. So we have a horizontal asymptote now, and it's at a -3, and because of that, all these dots were shifted a little, so it's all shifted down. And 2 should be at 1. But we still get a horizontal asymptote, and it still goes up rather quickly once you pass that, that anchor point. Okay? Alright, so in blue, the inverse. So we're going to swap x and y again. So at a -2.5, I have a -1. -2, 0, -1, 1. And then at 1, I should be at 2. So -2.5, -1, -2.5, -1. -2, 0 would be here, -1, 1 is here, and at 1 I'm at 2, so you're here. Okay, so hopefully you see that it does something like that over here, and then what happens over here? Okay, and this is one reason the asymptotes are important, because if you said that it does this, I would have to mark off. Okay, so let's take care of that line, erase it, and let's look at where the vertical asymptote should be. So swap x's and y's. So the vertical asymptote is at x is a -3. So if it's at x is a -3, and this is a good reason why you should draw it, then from here on you have to just make the line go down. You cannot cross this -3. Okay, and so remember that other line that I initially drew looked like this. Okay, so that one is impossible because you can't cross that asymptote. So draw the asymptote, use it to get the curvature somewhat correct. Okay, domain and range for both functions. So in red, the domain for exponentials is all real numbers, and the range for this one, y is larger than a -3. So the domain for the log was going to be x is larger than a -3, and then the range is all real numbers. Okay, we already did the asymptotes. So the only thing left then is to figure out what the actual function looks like. So x and y swaps, isolate, so add 3 first. So once the base is isolated, you can take a log base 2. So it's the log base 2 of the quantity x plus 3, and then equals y, so I'm going to write the y on this side, and there you go. So that is what this function looks like. Alright, last one. So in red, okay, so we're going to use a -1, 0, and 1, right? Well, not so fast. The reason we use -1, 0, and 1 is because this is supposed to be my anchor, right here. And the anchor occurs when your exponent is worth 0, but look what's happening here. If you use 0, you get 0 minus 3, that's a -3. So that's not the anchor. We want this to come out as 0, okay? So that means that I need to shift this, what means that this graph was shifted. And the shift comes from this part. We would like x minus 3 to be worth 0, so to get that we would have to plug in a value of 3 for x. So x minus 3 means it is a shift right of 3 units. Okay? So instead of a -1, a -1 plus 3 is 2. So we'll just erase it. So that should be a 2. And then we'll go from there. Okay, so if that's a 2, then this is a 3, and this would be a 4. And then that should work. So at 2, I get a -1 for the exponent, so that's a half. So a half minus 3 is a -2.5. So if I use 3, I get 2 to the power of 0, that's 1 minus 3, that's... Oh, I'm doing that wrong, aren't I? Let me go back. I did this twice. So plugging in a 2, let's do this right. So if I plug in a 2, I get 2 minus 3 here, that's 2 to the negative first, so there is your fraction. So if you plug in a 3, you get 3 minus 3, so that's that exponent of 0 that I was looking for, so there's your 1. And when you plug in your 4, 4 minus 3 is 1, and 2 to the first is equal to 2. So let's plug in a 5. So when we use an x of 5, we get 5 minus 3, which is squared, and 2 squared is 4. Okay, so at 2, I should be at a half. So at 2, I'm at a half. At 3, I'm at 1. At 4, I'm at 2. At 5, I'm at 4. So the exponential function looks like this. So other than that last little bit there, I did okay with that. So we'll just make that the arrow. So we do still have the horizontal asymptote. Okay, so the horizontal asymptote is still at y equals 0. Well, that means that this one has a vertical asymptote at x equals 0. So what kind of a shift? If that's a shift right 3, okay, what kind of shift does the log have? Well, we'll find out. So we're going to swap x's and y's again. So at a half, I'm at 2. At 1, I'm at 3. At 2, I'm at 4. And 4, I'm at 5. So at a half, I'm at 2. Then I'm at 1. Then I'm at 4. And at 5, I'm at... Sorry. At half, I'm at 2. At 1, I'm at 3. At 2, I'm at 4. And at 4, I'm at 5. So there's your asymptote. So it continues to curl that way. So I'm still not sure if you guys have seen the shift, what it actually happened, so we'll just solve for it. So what did we get in blue? Swap x's and y's, right? You can take the log. It's isolated, the base, so it's log base 2. So the log base 2 of x equals, the exponent comes down, but that's y minus 3. So you need to add 3 on both sides. So you get y equals, and then again I would do the plus 3 in the front, so it's 3 plus the log 2 of x. So the shift that occurred was up 3. Okay, hopefully that makes sense. Right is positive, correct? So that's a positive shift right, and then you get a positive shift up. Okay, domain and range. So let's do it backwards. Let's do the domain and range for the log. So the domain looks to be, you can use anything bigger than 0, right? So x is greater than 0. And for the range, I get all real numbers. So for the exponential, the domain would be all real numbers, which is true. You can use anything you want. And the range would be y is larger than 0, which it is. Okay? Alright, to summarize, so general rules, that means for an exponential that just has a base like this, and for a log that we just have a function looking like this, for example. So what happens? Well, okay, the domain for exponentials is all real numbers. The range from 0 to infinity, or you could say y is larger than 0, and it has a horizontal asymptote at y equals 0. For your logarithmic function, then you swap x's and y's, right? So we get from 0 to infinity for the domain, which could be written as x is greater than 0. The range is all real numbers, so again this was the domain, this is the range, and then the asymptote will be a vertical asymptote at x equals 0. And I believe that's it. Yep. Thank you.